I would like to welcome everybody. My name is Béla Kálnási, and today I am going to show how to perform safe hydrogenation with h-genie Mini Plus. Today's webinar has three major parts, and it takes about 60 minutes altogether. First section will be a short presentation from my colleague Gellért Sipos, who is the principal scientist of Cominex. Cominex is our sister CRO company. You will get more information in his presentation about our holding structure, safe hydrogenation, practices, and the basics of the flow chemistry. Second section is about the h-genie Mini Plus. I will show a brief technical overview and perform a reduction of 5-nitroindole, but we will go deeper when it comes. Third section will be questions and answers. Please, if you have any emerging questions during your webinar, do not hesitate to use the comment section. We try to give as many answers as we can, but if we run out of the time, we send you an email later. I will now pass the presentation to Gellért. Thank you all again for attending our webinar.
Thank you, Bill. Welcome, everyone. Thanks. So today I will talk about safe hydrogenation reactions using the h-genie Mini Plus. I will begin my presentation with a brief introduction on ThalesNano and its instrument portfolio. Then I will focus on some basic principles of continuous flow chemistry. Then I will give you a brief overview of hydrogenation reactions in continuous flow, and at the end I will give back the word to Béla, who will perform the live demonstration using the instrument. So ThalesNano and ThalesNano Energy are part of the DAR Holding group, which is a group of technology-focused companies. Most of these companies have some kind of interest in chemistry as well. Cominex, for example, is a chemistry service provider, mostly working with pharma companies, and their key specialty lies in the development of screening compound libraries. Agrothetis and DRGT are focusing on nanoformulation technologies for the agrochemical and pharmaceutical markets. InnoStudio is an R&D innovation research hub within the network, and the key research area there currently is space chemistry. A bit more about ThalesNano. ThalesNano was established 17 years ago, and it provides benchtop flow reactors for chemical industries. We are a market leader in continuous flow instruments. We sold over 1,400 instruments by now. Our first instrument, the h-genie, was awarded with an R&D Top 100 award, and more recently the h-genie, which I will show you later, received the same prestigious award. Here you can see our portfolio. Our portfolio covers quite a broad range in terms of temperature and pressure. Our instruments operate between -70 degrees and 1000 degrees Celsius in terms of temperature range, and the pressure range is typically between 1 bar and 200 bar, but some of our instruments are operating in vacuum. I will walk you through the instruments going from left to right. On the left you can see the ice cube, which is a flow reactor for low temperature reactions, which are typically exothermic ones, like lithiations, ozonolysis, or nitrations. If we move to the right a bit, then you can see the h-genie Pro here, and next to it the gas module. The h-genie Pro, I would say it's our flagship hydrogenation reactor, and the gas module provides you the opportunity to operate or to perform reactions not only with hydrogen but also with more than 14 other gases, And by using the gas module, you can, for example, perform oxidation reactions or carbonylations. On the right, you can see the Phoenix flow reactor, which is a high temperature, high pressure system capable of performing reactions up to 450 degrees Celsius and 200 bars. This instrument can be used for both homogeneous and heterogeneous reactions, either by doing the reaction in a coil or in a packed batch system. On the right side of the slide, you can see the flash pyrolysis platform, which is essentially a flash vacuum pyrolysis instrument. Flash vacuum pyrolysis is typically performed in the temperature range of 300 to 1000 degrees Celsius and under vacuum. For these reactions, the residence times are very short. Most reactions take place in less than a second. There are two more instruments which I want to highlight. One of them is the h-genie, a standalone hydrogen generator developed by ThalesNano Energy. So this h-genie can be used for both flow and batch purposes. And you can connect it with the Phoenix flow reactor, for example, and by this you can scale up your hydrogenation up to kilogram scales productivity per day. On the right side of the slide, you can see our photochemical reactor called the PhotoCube. This instrument is a multi-purpose reactor for batch and flow applications, and it has 8 integrated wavelengths in one single unit. As you can see, our instrument covers quite a broad range of applications. The H-Cube series can be used for hydrogenations, and other gases can be used as well with the help of the gas module. Exothermic reactions can be quite conveniently performed in the ice cube, and the Phoenix flow reactor offers you the opportunity to perform high temperature, high pressure reactions under endothermic conditions. The PhotoCube is our photoreactor with multiple wavelengths available, and the h-genie offers you a nice opportunity for scale up. In the upcoming weeks, we will have a series of these webinars, and throughout these webinars, you will be able to gain more knowledge on our instruments. So let's focus on continuous flow chemistry. What is continuous flow chemistry? Continuous flow chemistry performs a reaction in a continuous fashion by pushing through typically a solvent or a liquid stream through a coil or a fixed bed reactor. A simple flow setup just consists of a pump and the reactor, but there are quite a few alternatives, and high complexity setups can be built as well, including multiple pumps, reactors, and other accessories like mixers or back pressure regulators. There are a couple of fundamental differences between flow and batch chemistry, and I want to highlight a couple of them. If we are talking about flow chemistry, we usually don't say reaction time, but we use the term residence time, which means the time the reagent spent in the reactor zone. If you have, for example, two feeds, like in the scheme on the slide, then varying the flow rate of a single feed would alter the stoichiometry of your reaction, and by this the final concentration and the residence time as well. So in other terms, stoichiometry can be set by changing the flow rates or the concentration of the reagent streams. I want to also highlight the fact that temperature changes may require some adjustment in terms of pressure, especially if you operate above the boiling point of your solvent. And if you have a heterogeneous gas-liquid mixture, for example, pressure and temperature changes could affect the solubility of gases and therefore could influence the residence time as well. I highlight a couple of advantages of flow chemistry now. In flow setups, in microfluidic and mesofluidic reactors, we have a high surface to volume ratio, which helps us to have a precise control over temperature. And not only over temperature, but good mixing and mass transfer rates can be achieved as well. In a flow reactor, you can achieve homogeneous mixing just in microseconds. In addition to that, there is no headspace in a typical flow reactor, and using high pressure, high temperature conditions with low boiling point solvents like DCM, for example, you can heat up your reaction to, let's say, 150 degrees under, let's say, 15 bar pressure, and by this accelerate your reaction rate. Just think about the Arrhenius equation. The precise control over residence time gives us better control over selectivity. By changing the residence time or by altering the residence time, sometimes we are able to control the selectivity of a reaction between, for example, a kinetic or a thermodynamic product. Finally, you can gain a lot of advantage by performing dangerous reactions in flow. For example, you can in situ generate a hazardous intermediate, an explosive material or a toxic material, and use that hazardous intermediate in your next step just within seconds or minutes. So by this, you can avoid the buildup of large amounts of hazardous intermediates. Why would we perform a hydrogenation reaction in flow? There are a couple of challenges, mostly related to safety in terms of batch hydrogenations. Hydrogen cylinders represent a safety issue in most of the labs, as hydrogen is highly flammable. Therefore, in quite a lot of places, either dedicated hydrogenation rooms exist, or the hydrogen storage is completely separated from the application area. Another aspect lies in the technical side. When you perform a reaction using a heterogeneous catalyst, your workup usually starts with a filtration. In flow reactions, you can avoid this, as you will see it later. Finally, reaction times can range from minutes to days in batch reactions. In a flow hydrogenation setup, your reaction time is typically just in the second or minute range. The key advantages of the H-cube reactor series. You don't need a hydrogen cylinder for using the H-cube. Because there is on-demand hydrogen generation by an electrolytic cell which produces hydrogen by the electrolysis of water. So your process is inherently safer. There is improved heat transfer and mixing in the mesofluidic flow setup, and oftentimes we can achieve better selectivities than in batch reactions. Reaction times are typically very short, 30 seconds or so, and there is easy catalyst handling thanks to our CAD card technology, which I show you on the next slide. The CAD cards or catalyst cartridges are stainless steel tubes filled with a heterogeneous catalyst, and these tubes are sealed on both ends with a filter, so the solution can pass through the cartridge, but the heterogeneous catalyst will remain inside for the whole process. So in terms of handling pyrophoric catalyst, this provides you with improved safety. There is no filtration necessary at the end of your process. It has been demonstrated both in the literature, and you can find quite a lot of application notes on our website to gain information on what kind of hydrogenation reactions were performed in the H-cube series. But just to highlight a couple of examples, there are procedures for nitrogen or nitrile reductions, ring saturation of heterocycles, or protecting group hydrogenolysis, for example, debenzylation reactions. And this brings me to the H-cube Mini Plus, which is the smallest hydrogenation reactor in our portfolio. It is an affordable and easy to use reactor for both research and education. As I said, there is an in situ hydrogen generation inside this reactor, which also comes with easy catalyst handling thanks to our CatCart technology. So now I will give back the word to Bela, who will show you the instrument in details, and he will perform the reduction of 5-nitroindole. Thank you for your attention.
Thank you, Galet, for the presentation. Allow me now to show you H-cube Mini Plus in more detail. Catalytic hydrogenations are one of the most important technologies for the reduction of chemical substances, but is severely limited by the safety hazards of carrying out such a reaction. In response to these limitations and needs, we have developed the H-cube Mini Plus, a revolutionary benchtop continuous flow reactor that can perform a wide range of heterogeneous reductions in conditions of up to 100 bar and 100 Celsius degree, using the electrolytic reduction of protons as an internal hydrogen source. To this, we need only just deionized water with low conductivity. Today, we have prepared the setup of the system, primed the pump, and now we can just change from the fresh pure solvent flushing to the actual reactant. You can see the color of yellow of 5-nitroindole. The H-cube Mini Plus has a wide range of chemical resistance against several solvents such as methanol, ethanol, IPA, or THF. The reaction we are going to perform today is a 5-nitroindole reduction. The reaction conditions are as follows. We will pressurize the system to 70 bar, heat to 30 Celsius degree, and set the pump flow rate at 1 milliliter per minute. The catalyst we'll be using today is 10% palladium on carbon. The H-cube Mini Plus system is continuation of the H-cube series from ThalesNano. The main focus of the H-cube Mini Plus is on the hydrogenation of continuous flow of reactant. However, with judiciously selected catalysts, other heterogeneous reactions can be performed as well, such as cross-couplings, oxidation reactions, for example. Electrolytic water decomposition within the H-cube Mini Plus generates high-purity hydrogen in the required quantity, eliminating the need for hydrogen gas storage. The hydrogen gas passes through an automated water separator, which is responsible to eliminate any residual water from the gas stream. Then the hydrogen gas and the solution of the reactant are mixed in a fritted and preheated mixer. And the solution of the reactant are mixed in this mixer. And after it's transferred to the disposable cartridge CatCart that is preloaded with the required heterogeneous catalyst. I want to show you how does it look like our catalyst solution. These cartridges is compatible with the H-cube Mini Plus. This is the 70 millimeter CatCart. This is the 30 millimeter version, and now for this reaction we are using the 30 millimeter. And the only thing has to do with this, just you have to the right holder match to the right CatCart and then collected it into the collection vial. In most reactions, the only workup required is the evaporation of the solvent. The amount of collected product depends on the user and is only a factor of time. The limiting factor to pay attention is the catalyst activity. The continuous flow of reaction mixture out of the device allows the operator to carry out on-the-spot analysis of the resulting reaction mixture. Reaction parameters can be easily adjusting and using this touchscreen interface in order to achieve a better product yield. Now I want to show the liquid line of this setup. Here you can see the solvent feed from the pump. The H-Cube Mini Plus is supported by an HPLC type pump, which is a standard part of the package. From the pump, the reactant passes through the inlet pressure sensor. From this point, the solvent or liquid reactant passes through the mixer head. In the mixer head, where the built-in hydrogen generator introducing the hydrogen gas to the solvent. Together, the mixture of the gas and the solvent pass through to the heated reactor zone, where the cat cart is held. The actual reaction happens in the heated reactor zone, where the cat cars is presented, both the hydrogen and solvent pass through the catalyst bed. The reaction mixture will then pass through the back pressure valve. This valve has two major functions. During my presentation, that was enough time to go through the fresh solvent to the reactant. So now I want to change the product vessel to collect the actual product without any contamination of the washing procedure. So, on the left side of the H-Cube Mini, we can see product vessel and the water reservoir. Now, I would like to show the software as an initiative easy to platform. For this, we will using a software emulator and the help of my colleague just to see better resolution, all the text and the details. Here we can see the main and the info page of the software. On the info page, we can just follow all the reaction parameters and the condition and the set it parameters. If we go back to the main page of the software, we can just adjust temperature from room temperature to 100 Celsius degree. We can just set up system pressure from atmospheric pressure to 100 bar pressure. And we can choose hydrogen on or hydrogen off mode. The H-Cube Mini Plus is capable to produce 25 to 30 milliliter per minute hydrogen. Next to the hydrogen flow, we can just set up the flow rate. For this reaction, as we mentioned, we are using the same reaction parameters as you can see on the display. We have to mention the graph view. The graph view can monitor and follow all the reaction parameters at the same time. This useful option allows you to recognize any blockage and leakage during the reaction. And also there's a possibility with the USB stick to export the previous reaction data on a log file. So I'd like to ask my kind colleague to switch back to the picture of the H-Cube Mini Plus, because it seems our reaction has just finished. So, as you can see, from the starting material of 5-nitroindole, we just arrived for the change coloration from yellow to pale pink, this indicating a successful reduction. It seems we are finishing our reaction, so I suppose we can start question and answer. Thank you very much for your kind attention, and I hope we can see each other in the next webinar too.
Okay, so one viewer asked us to show the catalyst. Bela showed it since, but can you please again show the cartridges? Just from a closer distance.
Yes, we will ask Daniel, our colleague, to make a little bit zooming effect.
So what you see on the picture is 30, or in Bela's hand, there is a 30 millimeter long cartridge. And you might be able to see the seals if he turns it this way. So there is a stainless steel frit and a Teflon ring to provide sealing. Headspace, sorry, and that's the 70 millimeter long version. The 70 millimeter long CAD card typically contains 300 to 700 milligrams of material, depending on the actual catalyst. So, for example, René nickel is much heavier and denser than palladium on charcoal. Moving to the next question, what is headspace? Headspace is if you have a vial filled with liquid, the space above the liquid is headspace. So headspace is typically just air in a normal batch reactor. If you look at this system here, this is basically the headspace in the vial. Is it difficult to change the catalyst?
We can just show it really easily.
Yeah,
what do you think?
If you
Because
have stopped
it's just,
the reaction.
yes.
Yeah. So Bela will show you how to change the catalyst.
Yeah, we just used 30 Celsius degree for the reaction, so it's easily touched, but do not forget, because it can be more than 99, 100 degrees. But at this moment, we can just actually, sorry for my mistake. So I just removed the reactant, and so we have to just unscrew the cap if it's safe and sound. And now we have the possibility to remove the CAD card from the CAD card changer, and we can just use a brand new one. Of course, do not forget to remove all the labels before to use it, just to avoid burning in.
Okay. How many times the same cartridge can be used? There are no general rules for that. It will always depend on your chemistry. Sometimes a cartridge can be used for producing grams of compounds. Sometimes you can only use it to produce milligrams. For example, this nitroindole reduction can go on for hours, but if you have a compound which is a catalyst poison, that will quickly ruin the catalytic efficiency. So tell us about life of cartridges and storage requirements. For most of the catalysts, there are no specific storage requirements, but the general rules are the same as for any chemicals. So if you have a temperature sensitive catalyst, you should store it in the fridge, for example. Normally the cartridges come in a plastic holder. which you can see on the main screen at the moment. And after use, you can just put it back there. And once you don't want to use your cartridge anymore, you can place it in a deactivating solution. And there is a specific exemption, which is Raney nickel. Raney nickel catalysts come in a water-filled plastic holder. What is the typical substrate concentration in the solution feed? Typical substrate concentration can be anywhere between 0.01 molar and 0.5 molar concentration. Yeah. Can you comment something on conditions, that is flow rate determination, why and when is indicative to drop flow rate? So we have some general guidelines if you are not familiar with the instrument or with flow chemistry, which can give you a starting point to set up your first reaction. But generally, the flow rates would vary between 0.3 and 1 milliliter per minute for the H-cube mini. And basically, when you don't have high enough conversion, you either decrease the flow rate or you increase the temperature, or you do both at the same time. There are a couple of questions about the pressure. You can, so for example, is the system stable while working at low pressure, for example, less than 10 bar? You can operate the system at 1 bar, so at atmospheric pressure as well. In that case, all the produced hydrogen is just released into the system, so you might see some fluctuations, but yes, you can do it. Was the system already tested on benzyl protected compound that needed to be poly-dep protected? Did it show good yield? So the example which Francois mentions are benzyl protected sugars, for example. I'm not sure whether benzyl protected sugars were specifically used, but we have performed reductions on multiple functional groups at the same time. The next question is about pressure adjustment. You can set the pressure on this instrument up to 100 bar. Okay, if I missed any of your questions, can you please just type it in again? Or if something needs clarification, do that as well, please. events coming up. If you have any further questions, please send us an email which you can find on our website. And we will try to answer your question as soon as possible. Otherwise, thank you for your kind attention, and please join us on our next webinar as well. You will receive information about that in the upcoming days, either through email or through LinkedIn. Thank you again. Bye-bye.